Cybersecurity is one of the fastest growing and most respected fields today, and earning your CISSP certification can open the door to some of the highest paying and most trusted roles in the industry. But passing the CISSP isn't just about memorizing facts, it's about understanding how to think like a security leader. That's exactly what this course is designed to do. I will walk you through every domain, simplify complex topics, and share real world examples that will help you not only pass the exam but truly master cybersecurity. So, before we begin, like this video, hit that subscribe button, and turn on the notification bell. Hi everyone and welcome to our CISSP course. In today's video, we will go through Domain 3 Security Architecture and Engineering. This domain carries a weightage of 13% in overall CISSP exam content. So let's get started. Topics overview. So these are the topics that we will go through in these videos. Secure design principles, concepts of security models such as BIBA model, Bell-LaPadula model, and other security models. How to assess and mitigate vulnerabilities of security architecture, design, and solutions. Then we will come to our important topic, the cryptographic solutions. Then the cryptanalytic attacks are different attacks on cryptographic solutions. And last, we will study the site and facility security controls. We can also say these are the physical controls that are required, physical as well as logical control required for security of your physical facility as well as the site. So our first topic is secure system development. So the stages of a secure system development include design. These are generic stages. They may vary as per the requirement or as per the framework, but generally they are initial stage is the design of the system, and we develop the system. Before implementation, we test the system, then we finally implement the system, and then we go through the maintenance stage of the system, which is ongoing maintenance of the system. And when we finally the system run out of its life, you can say its useful life, it is decommissioned. So the key point or important point to remember and consider here is that integrate security early in the design phase. This is very important, and expect one or few questions that your exam, that the early you integrate security in your design or your system development, the better it is. So if you usually security is integrated traditionally after the system is implemented, but the more secure and better approach is to integrate security earliest, and the earliest phase here is the design phase. So we need to start integrating security here in this design phase. Why? So these are the reason for integrating security early in the design, because earlier integrating security is cheaper and easier to build security during design, rather retrofit it later. It ensures both user and systems component comply with security requirements, protecting confidentiality, integrity, and availability. So now coming over to some secure design principle according to ISO 19249, and these include the first principle is the principle of least privilege, which means granting only minimum access needed for tasks and only for as long as required. Least privilege limits potential damage from error and attacks. What does this mean? This means that let's suppose a user is doing something on a system and he or she, you can say, by mistake deletes something. So if the user was using, let's suppose, the admin account, or you can say the root account, which has high privileges, the damage will be very high if something unwanted is done through this account. On the other hand, if the user was using a simple account with limited privileges, for example, let's suppose we can say a guest account, even if something mistakenly is done, the damage will be limited. So that's why it is important that we always use non-admin and non-root account for daily operation and daily task or routine task. For example, in Linux, the sudo command temporarily grants admin rights. For example, we want to do something that requires admin credential. We just temporarily use the sudo command and the task is performed using the admin rights, and then the user reverts back to the user accounts to perform other tasks. Next design principle is attack surface minimization. Important one. This concept or this principle reduces all potential entry points for attacks. It minimizes the attack surface, and this is achieved by removing unneeded services, ports, or component and simplifying the workflow. For example, system hardening and disabling unused network ports. System hardening means, let's suppose you have a Windows laptop. So you can harden this laptop by disabling unused services, unused ports, enabling the firewall, installing the antivirus solution, etc. So next, the secure design principle is the centralized parameter validation. And what does this mean? This means that we need to use a single shared library to validate all user and system inputs. For example, we have a system. The system may be, let's suppose, a database. We are having a request from multiple sites, from multiple users. So it is important that we have a centralized system to validate all these input requests. So this prevents invalid or malicious data from entering the system. An example includes secure coding input validation or web application firewall. For example, if I give the example of the web application web firewall, it means that all the requests must go through this firewall, and this firewall basically validates the input for security and then passes it onward to the, you can say, the application, and then eventually to the database. So the centralized parameter validation is an important security rather than deploying decentralized security solution for each input or for each user. Decentralized input validation or parameter validation is a secure design principle. The fourth secure design principle is centralized general security services. This means managing core security functions such as authentication, logging, and key management centrally. Again, keep in mind that centralized security implementation is good, simpler, and you can also say cheap than doing this security implementation decentralized. So the why it is so? Because it simplifies management, it reduces errors, and improves consistency. An example is centralized access control system or SIEM system. So the SIEM is a security information and event management. It is a type of solution where the logs from all types from all the systems are centralized over here. You can say that the logs from network devices, logs from database, logs from, let's suppose, edge devices, let's suppose EDR, logs from clients, logs from server, all these are centralized at the SIEM solution, and it is where that the logs are correlated and make use of. And number 5 is prepare for error and exception handling. So systems must detect, handle, and log errors without leaking sensitive details. So when there is some error inside the system, we can see an error message. So the error message should be such that it does not reveal any sensitive information about the system. For example, its IP addresses, username and passwords, etc. The system should be designed to fail safe and stay secure during error or failure. For example, if a system is about to fail and it fails, it should fail safe without revealing any sensitive information. Example, ATMs reject overdraft attempts and display safe error messages. What does this mean? This means that if you try to withdraw an amount from the ATM which is more than you have in your account, the ATM would just display a message that, let's suppose, for example, insufficient balance in your account, rather than displaying other unnecessary information that could reveal inside information of the account or of the bank database, etc. Our next topic, and an important topic to consider, is the threat modeling. So the threat modeling purpose is to identify, analyze, and prioritize potential security threats and vulnerabilities during system design or operation to reduce risk. So in this topic, we will go through common threat modeling framework, and these are very important. The threat modeling frameworks include STRIDE, RED, and FASTA. So we will go through all these one by one. What does we mean by them? How they are used? So these are important. You should remember the abbreviation of these threat model as well as how they are used. What does they mean? So let's go and let's start with the first one, that is STRIDE. So STRIDE is developed by the Microsoft, and this threat model tries to help answer that what can go wrong by classifying 6 main threat types. You can see we have 6 alphabets in this this model name, and each alphabet basically points to a specific threat. And these threats are, so the S stands for spoofing, T is tampering, R is repudiation, I is information disclosure, D is denial of service, and E is elevation of privileges. So this model basically gives us 6 threat types, that what can go wrong with your system by classifying or speaking or analyzing these 6 threats. So the first one is spoofing. Spoofing means impersonating another user or system. So what are some mitigation against spoofing? Is first one is strong password. So someone, if your password is weak, someone may steal your password and then log into the system pretending to be you. So a mitigation technique, again, password guessing or password stealing, is to use strong password. Even more secure than strong password is MFA password, along with another factors such as biometric, fingerprint sensor, etc., and digital signature. So digital signature also gives us authenticity, origin of the user. Next is the T in STRIDE, which stands for tampering, and tampering is the unauthorized modification of data. And if you remember from our initial slides in domain 1, tampering is when integrity of information is compromised. So this threat basically compromises the integrity of data, and mitigation techniques includes access controls, logging, and integrity checks. Next is the repudiation, which is denying performing an action without proof. And again, the mitigation techniques against repudiation is secure logging and digital signature. As I said, that digital signature is used to for authenticity of someone. A digital signature belong to a unique user or to a unique system. So if an action is performed and a digital signature is used, the user or the system that performed that action later cannot deny having performed that action. So this secure logging, similarly through logs, we can determine the timestamp, the user, the action that the system or user performed. So this also gives us mitigation against repudiation. Next is the I, which is information disclosure. So this one is threat against confidentiality. It is leaking sensitive data to unauthorized users, and protection against information disclosure or confidentiality is to use encryption, DLP, data loss prevention, and access control. Next is the D, which is denial of service, and this one is threat against availability. So this one is C. No, this one is I. This one is C, and this one is our A, which is CIA triad. And as we studied initially, this was the initial. These are the some base pillars, but we need other security controls to protect our information as well, besides CIA. And the last one is, so the denial of service is making system unavailable to legitimate users. And we studied in our CIA triad, protection against DOS or denial of service is redundancy, filtering unwanted traffic, and rate limiting. So in denial of service attack, the attacker basically flood the system with attacks. If you rate limit the traffic, the flood of traffic or the DOS attack won't work. And last is the E instead, which is elevation of privileges, which is gaining higher privileges than authorized, and mitigation techniques against this threat are access control and input validation. So next, the threat model is DREAD, which is a quantitative threat rating. We will see how it is quantitative. As we study that the quantitative basically deals with digits or numbers. And the purpose of this model is to assess and prioritize security threats based on their potential impact and exploitability. So basically in this, as we said that it is a quantitative threat modeling, we give score from 1 to 10 to each of these, you can say, categories, uh, each of these threats. And then we aggregate them and we get a number. So you can say the threat that has the highest number then gets the higher priority for mitigation. So for example, there is a threat, and then for that particular threat, we get score for each of these. So in red, D is for damage, that how much harm can this threat cause. So if let's suppose our rating is from 1 to 10, so if it causes a harm of 1 or 2, it means it is less damaging, and if the threat causes a harm of, let's suppose, 8, 9, 10, it is very high damaging. What it measures business or operational fact, that how damaging it is for the business or business operations. Next is the reproducibility, which means how easily can the attack be repeated. And it measures the consistency and ease of replicating the attack. Next is the exploitability, which means how much effort is needed to exploit the vulnerability in the system. And it measures the skill, time, or tool required to carry out the or exploit the vulnerability. A in red is for affected users. So how many users are impacted or affected by that particular threat? So it gives the scope and reach of the threat. The more the user, the more damaging that threat is, or the more score that threat will, particular category of that threat will get. Last one is discoverability, which means how easily can the vulnerability be found inside the system. So it is the likelihood of discovery by attacker. So if it is easy to be found, it means it will get a higher score. And if it is very difficult to be discovered, it means it will get a lower score. So in this way, let's suppose we have 5 threats posed to an organization, and we assess each threat through this model, and each one of these get different number. For example, threat number 1 get 25 marks or 25 score, next one get 40, next one get 29, next one get, let's suppose, 90, and last one get 23. So how we then use this score for? Use this score for mitigation. So the 41, the threat having the 40 score will be mitigated first, followed by the threat having 29 score, then 25, 23, and 19. So our next threat model is the PASTA, which stands for Process for Attack Simulation and Threat Analysis. And its purpose is that it is a 7-step risk-based threat modeling framework which was developed in 2012 that aligns business objectives with technical risk and uses an attack-centric view to build effective mitigation strategies. So these are the 7 steps inside PASTA. Number 1 is define objective. Number 2, define technical scope. 3, application decomposition. 4, threat analysis. 5, vulnerability analysis. 6 is attack modeling, and 7 is risk and impact analysis. So now let's describe and goal of each stage one by one. So first one is define objective, which means identify key business goals, compliance needs, and conduct a preliminary business impact analysis or BIA. And the goal or the output of this stage is to understand what needs protection and why. As we studied in our first domain, BIA is basically input to other steps. So for example, if you are trying to carry out a business continuity plan, disaster recovery plan, first you carry out the BIA, which gives you the critical business processes that need to be protected first. Next is define technical scope, which is documenting all assets, system dependencies, and data flows within scope. So this gives us the full visibility of the environment, that what is the technical scope, what are the systems, what are the assets that needs, can say, protection, and it gives you the overall visibility of the environment. Number 3 is application decomposition, which is breaking down the application, mapping the data flow and trust boundaries, and defining the entry points. And the goal and or the output of this stage is to understand how and where data moves and who accesses it. Number 4 is threat analysis, which is gathering threat intelligence and identify potential attack scenarios relevant to the system. And the output or goal of this stage is to build a list of likely attack vectors. Number 5 is vulnerability analysis, which is to identify and map vulnerabilities in codes, systems, and networks to corresponding threats. And the goal or output of this stage is to correlate vulnerabilities with possible exploits. Number 6 is attack modeling, which is to simulate how attacks could exploit identified vulnerabilities, and the output is to evaluate likelihood and impact of each attack. And 7 and last stage is risk and impact analysis, which is to refine risk priorities and develop mitigation strategies for residual risk. And this stage creates an actionable risk mitigation plan. So next topic is Zero Trust Architecture or ZTA, an important topic. So this is ZTA or Zero Trust Architecture is defined by NIST publication 800-207 in 2020. And this term was originally coined by John Kinderweg in Forest Research 2010. So what is ZTA or Zero Trust Architecture? Zero trust means to never trust and always verify. Traditionally, the slogan was to trust but verify. But in zero trust, we say to never trust and always verify. No automatic trust for internal or external users. So traditionally, our internal users were trusted users, but in ZTA, there is no one to be trusted, including internal as well as external user. Every access request must be authenticated, authorized, and encrypted. So, traditionally, the initial request was authenticated, authorized, or encrypted, but later on it was not so. But in ZTA, every request must be authenticated, authorized, and encrypted each time. So it is designed to limit lateral movement and reduce blast radius of breaches. So these are important concepts. What does this mean? This means that if, let's suppose, one of your system is compromised, let's suppose this is your an application server, and then you have other server, other application server, you have database server. So the lateral movement is that if your one server is compromised, then this attack or this compromise of application should not spread to other server. So this ZTA basically reduces this, you can say, blast radius by limiting the attack to the only one machine on one server only, and limiting the lateral movement of this attack. So these are the core principle of ZTA. Number one is to always verify, authenticate, and authorize every request based on identity, location, device health, behavior, and data sensitivity. So it is not that you should authenticate only the username and password. You can use multiple criteria such as location, health, behavior, and sensitivity to authenticate the request. Use least privilege access, meaning granting minimum necessary rights, preferably on a just-in-time basis. What does this mean? This means that giving the rights only for that specific period of time for which it is needed and then reverting the rights back. Assume breach means afraid if compromise has already occurred, which is designed to contain impact. So key practices in ZTA or Zero Trust architecture is to enforce MFA or multi-factor authentication, verify device compliance before granting access, encrypt all internal communication, use microsegmentation to isolate network zones and prevent lateral movement. So what does microsegmentation mean? So traditionally we have the, let's suppose this is external boundary, which we usually call untrust, and internally we have the internal or the trust boundary. So all the system inside this trust boundary, they were trusted, and we have only two zones, one this external zone and internal zone. In microsegmentation, we further segment even our trusted or internal systems. For example, this system, and this system, these all are micro-segmented. And again, this is for the purpose that, as we studied in the previous slide, if one system is compromised, the attack or the malicious software, you can say, won't spread to other systems. And such and in such way the blast of the radius would be reduced. To protect data based on classification and tagging rather than location, employ real-time monitoring and analysis to detect anomalies and inform access decisions. Our next topic is Cloud Shared Responsibility Model, which is a cloud security framework that divides security duties between the cloud service provider CSP and the customer. So this one is also important. So in cloud, we have different models such as infrastructure as a service, software as a service, and platform as a service. And in each model, the cloud service provider and customer have different responsibilities. For example, in IaaS or infrastructure as a service, the cloud service provider is responsible for the physical host, the hardware, the network hardware such as switches, firewalls, and the hypervisor. So hypervisor is the virtualization software that is installed on the physical host, while the customer is responsible for the operating system, application, and data. So in the IaaS, customer has more responsibility than all the other models. In platform as a service, again, CSP is responsible for all these. These constitute the infrastructure as well as the runtime, while the customer is responsible for data, user access, and application code. So in past, customer is not responsible for operating system, rather than CSP is responsible for operating system. Infrastructure covers the OS, physical host, network, hypervisor, all this stuff. Software as a service, in this, the CSP is responsible for all the above things, including infrastructure, hypervisor, host, network, as well as the entire application, and infrastructure covers all these things, while the customer is only responsible for the accessing the application and the data handling inside the application. Our next concept is the defense in depth or layered security, which is a security strategy that uses multiple distinct layers of control to protect systems, ensuring that if one layer fails, other will provide protection. So these are used interchangeably. Sometimes they are called layer defense, sometimes it is defense in depth, and the term was first used by NSA. So we have already studied in, I think, in our first domain or in the second domain, where we saw that, let's suppose if we have our asset here, then we have multiple layers of security controls against this layer. So here we have some controls. Here. So if one layer fails, the next layers of control protect the system. If the next fails, the next layer protect it. So this protection mechanism is known as layer defense or defense in depth. And the key principles, let me clear the screen. So the key principles of layer defense or defense in depth is that we have multiple layers which combine technical, administrative, and physical controls. We have redundancy, which is overlapping controls to prevent single point of failure. Assume breach, so we design security with expectation that one layer may be compromised. Detection and response, which is prevention alone is not enough. Focus equally on monitoring and reaction. So now coming over to security models, which is an important topic, and our first security model is the Bell-LaPadula model or BLP model. So it is a confidentiality-focused security model that prevents unauthorized access to classified information, and it was developed by David Bell and Leonard LaPadula. That's why this model is known as Bell-LaPadula. So remember the point that it is focused on confidentiality of the information. So how does this work? So these are the core principle or properties of or rules of this model. Which first one is the SS property or simple security property, also known as no read up. What does this mean? This is that a subject cannot read data at a higher classification level. For example, a user that has secret classification cannot read top secret files. So, in this way, this model protects confidentiality because the top secret confidential data can only be viewed by top secret clearance user. If a user has lower clearance, such as secret or confidential, it cannot read or access the top secret files. Next is the star property, which is no write down, no read up, no write down. So a subject cannot write to a lower classification level. What does this mean? This means that let's suppose a secret user, which is a higher classification than a confidential classification, cannot write to a confidential file. Or similarly, you can say that a top secret user cannot write to secret level files because top secret has higher classification. Writing data to a lower classification would disclose that information to users having lower classification. Last one optional rule is the discretionary security property, which access is also controlled by an access matrix defining specific subject object permission. So for example, Department A officer can read secret files only within their own department. For example, if a user is in Department A and he has the security clearance of secret, it does not mean that this user can view file in Department B that has same secret clearance. This is also known as compartment. Term for this is used compartments or compartmentling. Compartment. I don't cannot pronounce the word right now, but there are compartments even within the same organization, and they have their own secret files. So one user from one department cannot access secret files from another, even if the user has the secret clearance. So this is the visual representation of the Bell-LaPadula model. So this is no read up. What does this mean? This means that the secret or confidential clearance user cannot read data from the top secret, and similarly no write down means that the top secret or secret cannot write data to the lower classification level that is confidential. So this is simple security property, this is star security property. Our next are, so these are some of the limitation of the Bell-LaPadula model. And the first one is that this model only focuses on confidentiality, not integrity. And it does not address covert channel, that is indirect data leakage through timing or resource use. So these are some of the methods to which data can be extracted from systems. One is timing technique and the other is resource use. So this Bell-LaPadula model is better suited for military or government environments than commercial systems. So this is mainly used inside military. As we already studied that the secret, top secret, confidential, these classification are government or military classification. Our next important model is the BIBA integrity model. As the name indicates, this one covers integrity. Bell-LaPadula was for confidentiality. BIBA is integrity model, and the purpose is it ensures data integrity, prevents unauthorized or untrustworthy modification. And the key rules of this model are First one is symbol integrity property, which is no read down. So subject cannot read data from a lower integrity level. So this prevents trusted processes from using unverified data. What does this mean? This means that if we have a top secret user, it cannot read from, let's suppose, secret, because that data is of less accuracy. You can say it is of less sensitivity, and if the top secret user reads that data, the integrity of the top secret data may be compromised because input is taken from less verified data. Star integrity property is no write up, so subjects cannot write data to higher integrity level, prevents less trusted user from corrupting critical data. Similarly, so the secret cannot write up means secret user cannot write data to the top secret files. Again, this is the visual representation. So simple integrity property is that the higher classification cannot read from the lower classification, which is no read down, and similarly lower classification level cannot write to the higher classification level, which is no write up, and this property is star integrity property. So an example of VBA integrity model is in a hospital system, doctor's diagnostic software operates at a higher integrity level while patient feedback forms are considered low integrity data. So according to VBA integrity model, the diagnostic system cannot read patient feedback data, that is no read down, to avoid basing medical decision on unverified information. Similarly, a patient cannot write directly to the medical database, nor write up, to prevent tampering with official medical records. So our next model is Clark-Wilson model, and this model is also integrity focused. So it is designed to ensure data integrity in commercial systems. So the previous two models, Biba and Bell LaPadula, they were mainly military focused. Clark-Wilson model was designed keeping in mind the requirement for commercial systems. So it is based on two main principles. First one is the well-formed transaction, which means that only authorized validated processes can modify data. As we said, it is integrity based. So only authorized and validated processes can modify data to preserve the integrity of data. And number two is separation of duties. So no single user can both authorize and execute a transaction. So we studied the separation of duties multiple times, that it is used to ensure prevention of fraud, and in extreme sensitive processes, the process is devised among multiple users so that a single person cannot both, such as in this case, authorize as well as execute that sensitive function. So in order for that sensitive process to be executed, it will take multiple parties or multiple users to collude or to conspire in order to do fraud. So the key components in this model are CDI, that is constrained data item, which is data whose integrity must be maintained. Then is UDI, which is unconstrained data item, which is input data not yet validated. IVP, that is integrity verification procedure, which ensures that CDIs, that is constrained data items, remain valid. And TP, that is transformation procedure, which is authorized process that modifies the constrained data items according to rules. So an example, in a banking system, a clerk enters a transaction which is unconstrained data items. So it is the input data that is not yet validated by clerk. Then a TP That is, a transformation procedure basically validates it and posts it to the ledger. So ledger here is the constrained data item, which is the data whose integrity must be maintained, and an auditor, that is IVP, integrity verification procedure, later verifies the accuracy. So our next model is Brewer-Nash model, also known as ethical wall or sometimes Chinese wall. So the purpose of this model is that it prevents conflicts of interest by restricting access based on prior data access decisions. What does this mean? We will know in a while. So the key concept behind this model is that access decisions are dynamic. They change depending on what information a user has already accessed. So core components of this model include: number one is the object, which is individual piece of data related to one company. Then we have the company data set, which is the all data or objects for a single company. And the third component is conflict of interest or COI class, which is all company data sets within the same industry or competing sector. So let's go through an example of this rule. So for example, if an analyst accesses Acme Finance, it is a fictional company. So if an analyst accesses Acme Finance data, they cannot access Ajax Finance data because now it belongs to the same class of interest class, but may access beta chemicals data, which is different class of interest. So since finance and finance belong to same COI, an analyst cannot access both due to conflict of interest. But if analyst accesses finance data from either Acme or Ajax, the analyst can then access the beta chemicals data due to different class of interest. So this is how this works diagrammatically. So we have, let's suppose, Acme Finance and Ajax Finance. So if analysts, let's suppose, accesses Acme Finance, and these two are basically belongs to the same conflict of interest class. So this is the wall that we are talking about, the ethical wall. If analyst accesses, let's suppose, Acme, there is this ethical boundary that the analyst should not now access the Ajax Finance, because this data can then be used for the benefit of either organization or insider trading, etc. Our next topic is memory protection inside information system security capability. So information system has security capabilities, and one of them is the memory protection. So the purpose of memory protection is that it prevents one process from accessing another's process memory, ensuring system stability and confidentiality. So this is how the memory protection works. So the operating system assigns specific memory areas to each process. The memory protection unit or MPU enforces these boundaries. And if a process tries to access unauthorized memory, the operating system blocks or terminates it. So what is the dual mode memory operation? So the privilege mode, are also known as the kernel mode. It is controlled by, so the OS controls memory protection and executes critical instructions. The next is the user mode, which is applications, where applications run with restricted access to memory and CPU instructions. Additional security feature is ASLR, important feature, which is address space layout randomization, which means it randomizes memory address location to prevent attackers from predicting where code or data resides, reducing the buffer overflow risk. Potential weakness inside memory protection in information system may be faulty hardware or operating system design can break the process's memory isolation. So vulnerabilities like Spectre and Meltdown that were discovered in 2018 exploited CPU design flaws to infer protected memory contents. Next is the secure crypto processor. So the purpose of secure crypto processor is to do certain cryptographic operations securely. So what is a secure crypto processor? A secure crypto processor is a specialized hardware module designed to perform cryptographic operations securely and protect sensitive data such as keys. So these are the core function of crypto processor: to generate two random numbers, secure key generation and storage such as private and public key, encryption and digital signing using internal keys also known as the private keys, and hardware acceleration of cryptographic algorithms. These are security features of the secure crypto processor. It is number one feature is tamper detection and response. So it erases sensitive data if tampering is detected. So if someone wants to physically tamper with the crypto processor, it has a built-in feature to erase the sensitive data or the keys. Physical shielding, so it prevents probing and signal eavesdropping. Trusted boot process, so it validates firmware and operating system integrity. Limited interface, so it reduces attack surface for improved verification. Now some types of crypto processor. So the proprietary crypto processors includes the Apple Secure Enclave. Open standard is TPM, defined in ISO 11889. So these are maybe standalone devices or smart cards. Now coming over to important topic, trusted platform module. As we studied, it is a type of secure crypto processor. So a TPM is a hardware-based secure crypto processor built into a system's motherboard that provides trusted computing functions as defined by ISO 11889. And the core functions of TPM includes attestation, which is verification of system integrity by hashing known good hardware and software states. Binding is encrypting data using keys tied to that specific system. And another feature or function is the sealing, which allows decryption only if the system remains in a verified and trusted state. So these are some of the features or some of areas that reside inside this TPM chip, such as the SHA-1, you can say hash generator, RSA key generator, storage root key, storage keys, encryption, decryption, signature engine, etc. Security services of TPM include that it generates cryptographic key pair. Private key never leaves the TPM. So it generates, let's suppose, public and private key, but the private key never leaves the TPM for obvious security reasons. It performs digital signing and encryption decryption securely within the chip and validates platform integrity to detect BIOS or firmware tampering. So what are some potential weaknesses of the TPM? First one is the manufacturer dependency. So the endorsement key security depends on the vendor trustworthiness. So this is the key that is generated by the vendor and then stored inside the TPM. So if the vendor is trustworthy, it means the TPM security is ensured. On the other hand, if you cannot trust the vendor, then the whole security is compromised, or you can say that the TPM security is then of no use because the root of trust is not trustworthy. Next is the software defect. So we may have the software defects where the TPM is used. For example, if the TPM is used in Windows based laptop and there is some defect in the window, again the TPM security can be compromised. An example is of 2017 Infineon law exposed private keys showing supply chain risk. So users were able to extract private keys from the TPM in 2017, thus compromising the security of the TPM. So the lesson is to always vet the hardware vendor and maintain supply chain risk management. Our next topic is HSM, that is Hardware Security Module, and definition is that the HSM is a dedicated device that securely generates, stores, and manages cryptographic keys and performs encryption decryption operation. And its purpose is to provide strong physical and logical protection for cryptographic material, reducing exposure to theft or tampering. What is the difference then between the HSM and TPM? So HSM, as we said, it is a chip that is part of a system. For example, it may be part of a server of a PC or a laptop. On the other hand, HSM is a dedicated hardware on its own, and its core purpose is to manage the cryptographic keys and cryptographic operations. And its common use is it is used by CAs or certification authorities to protect their root private keys, also by payment processor for secure symmetric keys of the card holder data, and in enterprises it is used to manage encryption for VPNs, archives, and internal traffic. So as you can see, the main purpose of this is to you can say manage and store the encryption keys. So key features include it is tamper resistant and certified. For example, it is certified FIPS 140-2/3. It offers secure application programmable interfaces for cryptographic services, and it operates as a standalone appliance and can be connected via network or USB connected. So, as I said, it is standalone as opposed to the TPM, which is part of a broader system. Our next topic is assessing and mitigating vulnerabilities of secure architecture or secure systems. So, the assessment methods include inspection. It may be manual, which is reviewing the design or configuration, or automated through tools. And the testing types include white box, which is when you have the full system knowledge. This type of test, for example, when done by the internal employees. Black box is when there is no internal knowledge of the system. For example, when you hire a third party to test your system which has no prior knowledge of your system, internal working. And gray box, it is between these two, which is when the user is having partial knowledge. For example, a third party audit team may be given some knowledge of the system that they are assessing or testing. So the combined approach of these improves assurance and identifies hidden vulnerabilities. So risk analysis is to assess impact and likelihood to prioritize the mitigation, and threat modeling identifies potential attacks, paths, and system weaknesses. So coming out to the database systems, that how we secure the system, what are some of the best practices to secure the system. So database system security overview. Database security extends server-based security principles. So additional control on the database depend on whether the database is network accessible. So if it is network accessible, we may have more control. If it is not network accessible, it is local, then we may have different approach for security of the database system. So non-network database server have fewer risks but still require hardening. So these are some of the best practices for database security to follow CIS database hardening guidelines, install and enable only needed component. This, as we study, this is also known as to minimize the attack surface. The less services or open ports you have, the less attack surface you have and the less threats you have to the system. Store data and logs on separate partition. Set strict file permission on database directory, logs, and certificates. Run database under a dedicated unprivileged account on a dedicated server. Disable command history and anonymous accounts. And avoid using environment variables or config files for credentials. So access control and authentication in database systems. So use TLS, that is transport layer security, for all connections and replication across untrusted networks. Assign unique certificates to each database instance. Change default passwords and use strong passwords or multi-factor authentication. Apply least privilege for user and admin roles. Avoid default roles. Define custom restricted roles per need. And remove unused or admin accounts. Use unique admin accounts per person to support separation of duties as well as accountability. So if you have named account after each admin, you know who is doing what. Monitoring and auditing in a database system. So enable and centralized logging for sensitive operations. Forward logs to secure monitoring systems such as SIEM. Protect logs from tampering by database admins. And so the SIEM gives you this function. If the logs are automatically forwarded to the SIEM solution, the database admin won't be able to tamper with the logs because they won't have access to the SIEM solution. Log security incidents with enough detail for forensic, such as for forensic, avoid passwords. Follow vendor specific security features, for example, Oracle Data Dictionary protection. Now, coming over to some an important topic, which is encryption approaches in database system. So encrypting the stored data is important, but encrypting data inside database requires specific and special approaches. And these include, first one is the full disk encryption, which protects data on the stolen or lost drive. So it gives no protection from logical attacks, which is because the system auto decrypts. What does this mean? This means that when a database is accessed by application, the data inside database is automatically decrypted, so it does not give logical attacks from, you can say, application side. Number two is file system level encryption, or you also sometimes known as FLE. So this encrypts at volume, directory, or file level. So this is again granular level or lower level. Full description is encrypting the whole disk, including all the data, file, directory, etc. While in file system level encryption, you can encrypt the data at file level as well as volume and directory level. Next is the transparent data encryption or TDE, which protects against operating system level access, but again, it does not protect from SQL injection or database admin abuse. And now coming over to some advanced encryption approaches, and the fourth encryption type as well, which is cell level encryption or CLE. This encrypts data at the cell or column level. You can say that this is the most granular encryption level, because you are now encrypting data at an individual cell or column inside the table. Enable fine grained key control, but adds complexity and performance cost. Of course, if you are encrypting data at such low level, granular level, it will hit the performance as well as add to the complexity. And fifth is the application level encryption. So encryption decryption handled by application logic layer. So database stores only encrypted binary data, and it is more secure but also complex and can limit database function, for example, searching inside the database, and encrypt as early as possible and decrypt as late as possible. So you should apply this approach when using the application level encryption. So what are some encryption design consideration in database systems? First one is the performance. So the cell level encryption may slow down the queries because you are encrypting each cell, or you can say column and rows. Another consideration is the backup. So protected under transparent data encryption or cell level encryption, FDE may not protect backup. So when database is encrypted using TDE or CLE, backups are encrypted. But if FDE or file system level encryption, the backups may not be protected. Compression, so encrypted data does not compress well, and so consider to decrypt first. First decrypt the data or the database, then compress it, and then re-encrypt it to avoid this scenario. But it also have the security risk because you are decrypting data, so you should keep this in mind. So now coming over to an important topic of this domain, which is cryptographic systems overview. So all cryptography can eventually be broken. The question is how much effort is required. So this is an important quote by Bruce Schneier. So what does this mean? This means that even if you use very strong encryption or long keys, it can also be broken, but it depends on how much resources you have, how powerful computer you have, and how much time and effort you can take to do the decryption. For example, now we are talking about quantum computing, and one worry about the quantum computing is that they can break the today's encryption standard very easily because they have immense power. So attackers weigh values of information versus effort to break encryption. So if the information is of high value, they may give the effort to break that encryption, and if information is of low value, they won't do the effort to break that encryption. So what does this mean? That if you have very sensitive data, you should use strong encryption algorithm as well as long encryption keys, so that it requires very huge effort or time to decrypt that information. So vulnerability may arise from encryption or cryptographic algorithm as well as the protocol weaknesses. How do you implement them, as well as key management vulnerabilities? As we studied, if you use the HSM, you may have less vulnerabilities inside key management. But if you use simple some software solution, you may have key management vulnerabilities. So algorithm and protocol weaknesses are to use, you should use only algorithms that are proven, reviewed, and standardized. For example, the AES for encryption and SHA-2 for hashing. Avoid algorithms with known flaws or backdoors. For example, dual ECDRBG. An example of a weak algorithm or compromised algorithm is WEP, which is wired equivalent privacy used inside Wi-Fi. It is weak, 24-bit, and plus also flawed, and it can be easily decrypted. So you should never use such algorithms that are proven to be weak and compromised. So cryptography also weakens over time due to increased computing power, as we were talking about quantum computing, improved cryptanalysis methods, and as we said, quantum computing threads. So you should use life cycle management, that is re-encrypt long-lived data with new standard. For example, if you had stored some data and encrypted it with the DAS or data encryption standard, you should re-encrypt that data now with the AES, which is more strong encryption algorithm as compared to the DAS, which was used in the past but is now weak and compromised. What are some implementation weaknesses? So you should use trusted published cryptographic libraries and never self-developed. You should not use your own developed because they may be weak, you may never know. But the well-trusted and well-tested public library should be used. Case study is the heartbleed scenario where TLS heartbeat flaw, I think heartbleed flaw leaked server memory including private keys, and it affected this much secure websites. There are some side channel attacks which applied power consumption, timing, electromagnetic emission. So when a server is running, the power consumed by the server, the timing of these power consumption, as well as the electromagnetic waves emitted by the server, the data from these can be used by hackers to deduce or infer the algorithm use or other information. The mitigation of these flaws include using constant time comparisons to avoid loops or lookups based on secret data, using cryptographic grade random number generators, and validate compiler behavior. So what are some key management vulnerabilities? So always follow NIST special publication 80133 for key generation. Use key rotation and avoid key reuse. You should change the key and rotate them frequently. Store keys securely using key management software, cloud KMS, and more importantly, the dedicated hardware security modules. So protect against insider threats via dual control and segregation of duties. As we stated, for example, you should not give the complete key to one person. Rather, you can divide and give one portion of key to, let's suppose, one person and another part of portion of key to second person, so that it takes at least 2 person to do encryption or decryption. Ensure availability of key material, log key operations for accountability, and automate key management to reduce human error. So the tools or hardware security modules, you can say they are more secure because they are less prone to error as compared to manual human efforts. Our next topic is Industrial Control System or ICS overview. So industrial control system automate industrial processes such as manufacturing, utilities, power, and HVACs. So focus on integrity, availability, and safety. Historically, these systems are isolated, but now increasingly connected to the network. So it means they are now more exposed. And some example of frameworks include ISA IEC 62443, which define secure industrial control systems procedures. NERC CIP, which is mandatory for power infrastructure inside US and Canada. NIST SP 800-82, which is a guide to securing industrial control system, and ERNCIP, which is EU's critical infrastructure protection. So some industrial control system security challenges. First one is the patching difficulties. So the industrial control system they operate continuously without any break. They are almost located remotely at remote sites. For example, sometimes they may be offshore, and you cannot take risk of the downtime. They most often use the default credential and they are often left unchanged. So they have a long life cycle as compared to other IT systems such as server and PC, 10 to 20 years versus 3 to 5 years in IT systems. And air gap network not always reliable. What does this mean? This means that the industrial control system may be air gapped. Air gapped means that they may not be connected to the network or to the internet, but that does not guarantee the security. An example is the Stuxnet malware, which was used against Iranian centrifuge, which were, of course, air gapped, but the malware was conveyed there or it reached the Iranian centrifuge through an infected USB. So the air gap was breached through a USB. A USB was connected to, let's say, you can say, an engineer laptop, and that laptop was connected then to the centrifuge network, and the malware thus spread to the this air gapped network. So what does this mean? This means that you should not only rely on the network security, but other connectivity such as USB, the operating system, the software that you are using inside air gap network as well. What are some best practices for securing industrial control systems? So apply firmware and software updates whenever feasible, maintain strict physical security for devices, enforce network segmentation and use firewalls and proxies. For remote access, use VPNs or web proxies, use dedicated maintenance systems. So when no internet or personal use, so the systems that are used for the maintenance, for example, the PC or laptops, they should not be your personal system and they should never be connected to the internet. Security awareness training for operator and technician, which is important one, because remember, humans are always the weakest link in the security chain. Our next topic is the distributed systems. So distributed systems are a group of interconnected systems that operate together and appear as a single unified system to users. An objective of these systems are reliability, because they continually operate despite failure, performance, optimized resource utilization, and scalability. They can handle increased workload efficiently. What are some security challenges of these distributed systems? So they have large attack surface due to multiple interconnected subsystems, encryption and authentication needed between components to prevent interception and spoofing, denial of service risks targeting communication links or individual subsystems, inconsistency issues, that is split brain issue between different systems if communication between them is disrupted. Heterogeneous environments make patching and configuration management harder. Geographical distribution complicates applying consistent physical and personnel security, and data sovereignty and privacy laws restrict cross-border data transfer. Our next topic is the Internet of Things, or IoT. So IoT is a network of physical devices such as sensor, appliances, machines that are embedded with the software that enable them to connect and exchange data over the internet. So nowadays, almost all things are smart, such as your car, your washing machine, your refrigerator. These all things can be part of Internet of Things. Example include smart home devices, medical sensor, routers, CCTV cameras, and industrial controller. So what are some IoT security principles from manufacturer's perspective? So These are the things that should be done to conduct threat modeling during design and development of these Internet of Things, to follow OWASP and SANS secure coding guidelines, enforce default password change before device activation, enable automatic firmware updates, design for secure initialization and firmware integrity checks, and balance usability versus security. Ease of use must not mean ease of compromise. So, what are IoT security from users' perspective? Again, to change default credential before connecting the Internet of Things devices to the Internet, keep the firmware updated, and best thing is to enable auto updates, or you can also check it manually if this is not possible. Place all the IoT devices behind a firewall and should not be directly connected to the Internet. Segment the network means to isolate IoT devices from other sensitive systems. Use reverse network address translation or proxy authentication for external access, and secure your router or proxy, that is to change the default credentials and apply vulnerability or security patches. So key security principles include defense in depth. As we already studied, defense in depth means to apply multiple layers of security such as firewall, proxy, and segmentation. Least privileges, restrict devices access only to what's needed. And zero trust is to do not rely on network location, authenticate every user and every device, even if they are trusted or your internal devices. Our next topic is microservices architecture. So it is a modular design approach where an application is divided into independent, loosely coupled services, each running its own process and communicating via lightweight protocol, for example, REST APIs. So it is in contrast with monolithic architecture. In monolithic architecture, we have one single huge architecture. So monolithic is one large single unit code base, for example, Microsoft Office. It is one application, one software, a big one. And microservices are independent modular services. For example, AWS architecture. In AWS, we have numerous small services or modular services. What are some key security principles in microservices? First one is isolation. So each service should be independent, deployable, modifiable, and removable without affecting other services. And to contain vulnerabilities within one service to prevent system-wide impact. As we studied in microsegmentation or segmentation, the microservices, since each service is independent, so the vulnerabilities are, you can say, weaknesses in one service should be limited to that and should not spread to other services or system wide. Again, defense in depth, apply multiple security layers at service and network levels and protect both individual microservices and their inter-service communication. API security and gateway. So APIs are the most vulnerable points in microservice environments. So use an API gateway to act as a single entry point for all client requests. Enforce authentication, rate limiting, and input validation via API gateway, and hide internal microservices behind a firewall. Next, our next topic is containerization. So a container packages an application and its dependencies into a single lightweight unit that runs consistently across environment. For example, the service or the container package can be run on-prem, inside cloud, or both at cloud as well as on-prem. So key point in containerization is that it uses the host operating system kernel instead of a full operating system, unlike VM. So in virtualization or in virtual machine, each VM has its own operating system. In containers, the container package does not have its own operating system, rather than it uses the host operating system kernel, enables fast, consistent, and portable deployment, commonly managed using Kubernetes, and it supports both monolithic and microservice applications. So what are some security concerns in containerization? First one is the compromise of container images and repositories. So use SIGN-based images from trusted sources, apply vulnerability scanning and patching, and maintain configuration management and version control. Number two is misuse of containers or host compromise. So avoid running containers with the privileged flag. Apply RBAC or role-based access control for image access. Secure the host operating system and run only necessary services. And restrict container-to-container communication. That is the principle of least privilege. Another concept is the serverless computing, which is a cloud model where the provider manages the server, automatically provisioning and scaling resources as needed. The user focuses only on writing and deploying the code. For example, AWS Lambda, Azure Function, and Google Cloud Function. So key benefits of the serverless computing is that you don't you don't need to do any server management. So cloud provider handles all the provisioning, patching, and scaling. Ephemeral function means that they are short-lived. Code execution reduces attack persistence. So the host environment is only needed during the code execution. So this reduces the attack persistence, or you can also say attack probabilities. Granular access control, so small code bases allow tighter permission, and reduced customer responsibility, so the provider handles operating system and runtime security. So what are some security concerns in serverless computing? First one is the broken authentication. So weak or misconfigured authentication mechanism is a security risk. Over privileged functions, excessive permissions, and roles, complex attack surface. So multiple interconnected functions increase the exposure. So what are some best security practices in serverless computing? First one is to enforce least privilege, grant each function only necessary permission, enforce code integrity, scan for vulnerabilities and configuration issues, enable runtime protection. So this detect anomalies, errors, or suspicious events, and use provider and third-party security tools to leverage AWS, Azure, or Google Cloud Platform built-in monitoring and external solutions for added defense. Our next topic is embedded systems. So embedded systems are specialized computing components within larger mechanical or electrical systems performing dedicated function. For example, in cars, ATMs, routers, medical devices, or appliances. Common uses of embedded systems include they are used in domestic appliances such as TVs, refrigerator, washing machine, in office equipment such as printer, scanner, inside network devices such as routers, firewall, automobiles, ATMs, medical devices, and industrial systems. So some attack surfaces and examples in embedded system. So these are the types, then the description, example of the attack, and how to mitigate them. So attacks related to the user interface is that manipulating the controls or hidden administrative functions. An example attack on user interface could be pressing button sequences to unlock specific features. And mitigation include the firmware review and fuzz testing. Next is the physical, so tampering with the device casing or service ports. An attack example include exploiting a voting machine via its management ports, and mitigation is tampering detection, strong locks, and epoxy. Next is the sensor, and description is to interfere with the input sensor. Example attacks include skimmers or shimmers on card reader, Tesla key relay attacks, and mitigation includes sensor hardening, encryption, and shielding. Next type is the output, which is controlling the actuators directly. Example attack include forcing door locks open via power injection, and mitigation includes secure cabling, physical protection. And last one is the processor, which is direct chip access or firmware manipulation. An example attack include loading RUG firmware onto the processor, and mitigation include signed firmware, encryption, and update. So what are some security considerations for the embedded system? And they are to use digitally signed firmware to prevent unauthorized update, that is to preserve the integrity of the embedded system firmware, apply cryptography to protect firmware and its communication, implement tamper evident and tamper resistant designs. We are talking about physical tampering with the embedded system, and plan firmware upgradability or add compensating control if patching is not feasible. So it is recommended that you upgrade firmware regularly, and if this firmware upgradation is not possible, then you need to add some compensating control, and these may include installing a firewall in front of the embedded system, segmentation, network segmentation, etc. So our next and important topic is now cryptography. So what are initially some core cryptography definitions? So these will be used throughout our upcoming slides about cryptography. So going through quick definitions of these terms, plain text is the original readable message, such as these slides. It is a plain text. It is not encrypted, not 012 or something like that. You can make sense of these reading. So it is a plain text. Clear text is the readable message not meant to be encrypted. So let's suppose this, I transfer this message to someone without encrypting it, then we can say that I sent the message in clear text. Okay, I hope this is understandable. Number 3 is ciphertext, which is encrypted unreadable form of the message. For example, if I encrypt this message, these two lines, using the AES encryption, then it will result something like this, you can say, and it won't make any sense. They are unreadable messages that you encrypted. Encryption is the process of converting this plain text into ciphertext. Decryption is process of converting ciphertext to plain text. Cryptographic algorithm is math function used for encryption decryption. So when we do encryption and decryption, we do it through cryptographic algorithms such as this one. AES is example of a cryptographic algorithm. Key is the secret value controlling the cryptographic algorithm. So when we encrypt the messages or text or data, then we use the algorithm plus a key length. For example, we may use 256-bit key length, and this secret key is the, you can say, the secret sauce that do the magic. You can reveal everything, the cryptography algorithm, the everything else about these all encryption function, but you need to keep secret only one thing and you will be good, and that is your key. We are talking about the symmetric key, or in public key cryptography, the private key. it should always be secure. If it is revealed, then everything is all these encryption algorithm and your data is then can be easily decrypted using this key. Next is the key cryptographic life cycle considerations. So what are some considerations during cryptography life cycle? First one is the algorithmic algorithm selection. So we have multiple type of cryptography algorithm. It may be symmetric, which uses same key for encryption, decryption. So we will study these in detail in the upcoming slides. Asymmetric is the public key cryptography, in which we have two keys. One is public, one is private. And then hashing is a one-way cryptographic function in which we convert a variable length of data into a fixed length of hash. It is mainly used for integrity, as we already studied. So some cryptographic algorithm examples such as AES, which is a symmetric algorithm, RSA is asymmetric, SHA is example of hashing, etc. Another thing that is used, as I already told in previous slides, is the key length. For example, AES-256 means that we have a key length of 256 bit. RSA-2048 means that we are using a key length of 2048 bit. So these are important consideration when using cryptography, when selecting cryptography process. So use cases of the cryptography. So symmetric encryption is used. It is fast. So you can say it is used when we have very large amount of data or bulk data because it can encrypt it fast. It is good for data at rest encryption and in transit as well, but requires secure key exchange. What does this mean? This means that since in symmetric key we have same key for encryption as well as decryption. So if we have a party A and a party B, and party A want to send a message to B, then the first thing to consider is how to send that same symmetric key to B. Because if party A encrypt message with a key, let's suppose key 1, the same key must be used by party B to decrypt it. So how do we exchange? We will study this in the upcoming slide. This is an important consideration. This consideration is not required in public key cryptography. We will how it is done in public key. We will study this also in the upcoming slide. So hashing is a one-way function for passwords, data verification, and no decryption needed. One way means that you can say encrypt or change your data into a hash, but it is not reversible. You do not decrypt that back, or you do not reverse that hash back to the original data. Then how does we use hashing? We compare the two hashes. For example, you are sending a message 1, you take a hash of this, let's suppose hash 1, and you send it to, let's suppose, a party B. You also send the message in, let's suppose you can say in plaintext or encrypted to party B. The party B then hash the message again. Let's suppose here is hash taken by party B, hash 2. And then the party B compares this hash that it received as well as the hash taken by the party B from the original message. If they both are equal, then it means the message is original, it is not tampered with, it is not alterated, and that how the hashing works. We will study about it in detail. Tokenization is replacing sensitive data like PAN with tokens to reduce exposure. So as we studied in our, I think, domain number 1, tokenization is when we have personally identifiable information and we want to make it confidential, we can replace the sensitive data with tokens. Number third consideration is the performance and constraint. So let's suppose for Internet of Things and edge devices, these devices has very low processing power. So we need lightweight cryptography algorithms, hardware support. So some CPUs such as Intel, AMD or ARM, they accelerate specific algorithms like AES. They had built-in algorithm acceleration for specific algorithm. So you can need to consider these things in mind. Key length trade-off. So longer the key, more is the security, but also it requires greater processing power, and so your overall performance will be slow if you use longer key length. So you need to have a trade-off between security as well as performance. Blocks versus stream fiber. So these are two types of cipher. How you do encrypt data. So block ciphers encrypt fixed sized blocks. For example, AES, they encrypt data in fixed bulks or sizes, and it is commonly used for data at rest. Stream fiber encrypt data bit by bit, and it is common for real time communication, such as for serial communication, you can say. Fifth consideration is the mode of operation of the cryptographic algorithm. It may be ECB, that is electronic code book. This is simple but insecure because it reveals patterns. For example, if you have same type of text, let's suppose hello, it will always result in same type of, you can say, encrypted data. So it reveals pattern which is unsecure. CBC, that is cipher block chaining. It is more secure because it uses initialization vector, and due to this initialization vector, same text does not always result in same encrypted data. Next is the cyber feedback. So it turns block cipher into stream fiber. So for example, if you have block cipher, the cipher feedback basically turns it into, you can say, stream fiber. So some important principles. First one is the cryptographic agility. Algorithms can become weak over time. For example, the DAS, RC4, and SHA-1. These have become weaker over time, and nowadays they are insecure and deprecated. They cannot be used anymore. Key management is critical for security. It includes generation, exchange, storage, rotation, and destruction of keys. And data lifetime is the long-term archival may require stronger keys and algorithm. So for example, if you need to archive the data for long term, you should use stronger keys and algorithm, because as we said in our first principle, algorithms also become weak over time. So you should use strong algorithms so that they test the time period. Cryptographic methods overview. So what are some cryptographic methods or cryptographic algorithms? Important topic. So the purpose is to protect confidentiality, integrity, and authenticity of data. The purpose of cryptography. So what are some use cases and which type of cryptographic method is used? First use case is, let's suppose, confidentiality of stored data. We need, and we use, as we studied in previous slide, for data at rest or for stored data, we use symmetric encryption. It is strong, it is fast. Confidentiality of data in transit, again we use symmetric for data encryption. We also use asymmetric along with symmetric, but this one is mainly used for the exchange. As we studied in our previous slide, that in symmetric we need to have same key for encryption as well as decryption. So how do we exchange the key securely? It is done through the asymmetric algorithm. So symmetric is used for the data encryption along with asymmetric for the key exchange. So we can say that we use the hybrid approach. Identity verification is done through the public key infrastructure or PKI. Data integrity, for data integrity, we use hashing and message authentication code. For password protection, we use hashing with salt and pepper. So as we studied in the previous example, if we don't use salt with hashing, same password will always result in same type of hash, which is vulnerable to different types of attacks, such as Rainbow table attack. For example, if your password is 123 and you take a hash of it, the hash, I'm giving just an example, without salt, this password will always result in same hash. So it is vulnerable if uh, the attacker get hold of the hashes of the messages. It can easily be deduced that which type of passwords are being used. And if you use salt and pepper with the hash, same password will not result in same hash each time, because besides this password, salt means, let's suppose a true random number is added with, let's suppose 146 ABC. This is a salt that is added, and so it will result in something else. Non-repudiation means that if a user or system performs some certain action, it should be made certain that they later they cannot deny having performed the action, and it is done through digital signature. So now coming over to the different encryption algorithm. First one is symmetric. These slides are important. So symmetric algorithm or symmetric encryption uses same key for encryption as well as decryption. It is fast and efficient for bulk data. These are very important for from exam point of view. You should keep this in mind that it is fast, and since it is fast, it can be used for bulk data encryption. Example of symmetric encryption include DES, triple DES, AES, and RC algorithm. So DES is no longer used. Triple DES is also not recommended. The recommended standard for encryption AES or for symmetric encryption is AES Advanced Encryption Standard. But as we already studied, for symmetric key, one important consideration is to securely share the symmetric key between the two parties. And for this, we then use asymmetric or public key encryption. So symmetric encryption may be stream or block cipher. So in stream fiber, the symmetric key encrypts data in bit by bit or byte by bit using key stream. For example, an example of stream cipher, symmetric stream cipher is RC4, and its use case is to encrypt data in real time and low CPU, and it is used in low CPU devices. Block cipher, as we studied, it encrypts fixed sized blocks, for example, AES and DES, and it is used for file encryption and VPN or virtual private network. What are some common symmetric encryption algorithms? And these include DES, data encryption standard. Key size is 56-bit, but this is obsolete, deprecated, and should not be used anymore. Triple DES is key size maybe from 112 to 168-bit. Again, it is also deprecated and should not be used. The go-to standard is AES Advanced Encryption Standard. Key size may be 128, 192, or 256, and it is the current standard. RC2 and RC4 key size is variable. It is also insecure and should not be used. RC5 and RC6, again, their key size or key length is variable. It is secure, and RC6 was basically the finalist for during the selection of AES, or you can say it is as strong as AES. So our next important encryption type is asymmetric encryption, also known as public key cryptography. And this one solves the key distribution problem of symmetric key encryption. So this is important point, keep this in mind. Asymmetric encryption or public key cryptography uses two keys. Public key is used and shared openly, and private key is kept secret. So if you encrypt data with the public key, only private key can decrypt it. So it gives you the confidentiality. And if, for example, you can also use this for encryption. For example, your public key is with everyone. They can send you data encrypted with public key, and only you can decrypt it because only you have the private key. On the other hand, if you encrypt data with your private key, again, it can be decrypted with the public key. Everyone can decrypt it. Then how does we can use this functionality for authentication and non-repudiation? It means that since only you have the private key, if the data is decryptable with public key, it means it must be sent by you. The other case is that your private key is lost or compromised. So it is used for authentication, non-repudiation. Based on mathematical trapdoor function, easy one way, hard to reverse. So there is a mathematical calculation behind this asymmetric encryption. So that's why it is easy one way but hard to reverse. These are mathematical formula using the logarithmic calculation and prime numbers, etc., to calculate the private and public key and how they interact with each other. Some common asymmetric algorithms include RSA, and RSA is used for encryption as well as digital signatures. As we studied, the digital signatures are used for authenticity. And it is based on, as I said, factoring large prime numbers, and it is most widely public key in algorithm used. Next is the Diffie-Hellman-Merkle, and it is used for key exchange, and it uses discrete logarithm, and it generates shared symmetric key. So as we studied that public key in public key cryptography is used for symmetric key sharing on symmetric key exchange. So it is basically the Diffie-Hellman-Merkle algorithm that is used for generating the symmetric shared key and sharing with the parties. Algamel is used for digital signatures and key exchange, and it is derived from Diffie-Hellman. It is slower but flexible. ECC, important one, elliptic curve cryptography. It is used for encryption, signatures, and key exchange, and it is based on elliptic curve method. So it has smaller keys but faster performance. So as we studied in our previous slides, that for Internet of Things or edge devices, as well as you can also say embedded systems, these systems has low resources, or you can say low processing power. So for this system, it is recommended that you use ECC because they are faster, having faster performance with smaller keys. So this is an important point to keep in mind and to remember. If you come across a question in your exam and you are given multiple, let's suppose these 4 algorithms, and you are asked about which algorithms would suit best to be used for IoT, edge, or embedded system, then your answer should be ECC or elliptic curve cryptography. So ECC advantages are that they have smaller key size but smaller key size with strong security. So that's why their computation is faster. and it is efficient for mobile, IoT, and low power system, as I already said. So, for example, 256-bit ECC is almost equal to 3072-bit RSA in strength. So that's a huge difference in key length, but they have the same strength. So in summary, asymmetric encryptions enable secure communication without sharing the secret key. Public key infrastructure manages key and certificates, and often combined, the public key encryption is often combined with symmetric encryption in real-world system for performance. That is hybrid encryption, because public key encryption is used for key exchange, while symmetric encryption is actually used for the actual data encryption. Quantum cryptography. So it is a cryptographic method that leverages the laws of quantum mechanics to ensure secure key exchange and detect eavesdropping. What is quantum key distribution? It uses quantum particles like photons to transmit secure keys. Any interception disturbs the quantum state, revealing the eavesdropping. So now it is very easy using the quantum cryptography that if a key is intercepted, the quantum states changes and it can be easily revealed that the key was intercepted. If interception is detected, the key is discarded and a new one is generated. Once a secure key is confirmed, data is encrypted using symmetric encryption or one-time pad. So why it is so powerful? It is because security is now based on laws of physics, not mathematics, and it is immune to future computational power and quantum computer-based attacks. So the current cryptographic algorithms that are based on mathematics, they both are prone to computational power as well as quantum computer-based attacks. So post-quantum cryptography, that is quantum safe cryptography. So with quantum computers emerging, classical algorithms like RSA, ECC may be broken. Quantum safe, quantum safe cryptography uses new mathematical approaches resistant to quantum attacks. At CQSC, that is Quantum Safe Cryptography Group, develops standards for future-proof security. So summary of the quantum cryptography. So quantum cryptography uses quantum mechanics for secure communication, and its key advantage is that it detects eavesdropping, because if intercepted, the quantum state is changed, and so it is easily detected. The interception is detected. Quantum key distribution is used for secure key exchange, and key advantage is that intrusion is easily detected. Quantum safe cryptography protects against quantum computers, and it is for future resilience. Our next important topic is PKI, or public key infrastructure. So PKI provides a trusted framework to manage, distribute, and verify public keys, ensuring that a public key truly belongs to the claimed entity. So how does PKI work? So this is, we will explain it with this example. So step one is, let's suppose Alice creates a certificate signing request, or CSR, to the CA, which contains her identity plus her public key, and it is signed with her private key. So since Alice's private key is only with Alice, it makes sure that the public key actually belongs to her. So this is what the CSR contains. It is sent to CA. In step two, the CA basically verifies LS identity based on LS public key, which was encrypted with or signed with her private key. And the CA signs and issues a digital certificate binding her identity to her own public key. And now, finally, Bob, which is a third party or another user, if Bob trusts CA, it means therefore Bob trusts LS certificate and public key. So this whole method, this whole concept is based on CA's trust. If CA is trusted, So are other people, other individual, other parties that have received certificates from the same CA. So X.509 digital certificate structure. So you can say this is the certificate that is issued by CA, and this certificate includes the version and serial number of the certificate, signature algorithm that is used for signing the certificate, CNM, which CA issue the certificate, validity period of the certificate, the owner, subject or the owner, and the public key usage and extension, and CA's own digital signature. So CA digital signature is used to verify the CA. What are some certificate types inside the PKI? So it may be personal or organizational, which is used for email, code signing, and identity. An example is digital certificate of a specific user. Another certificate type is a certificate of the web server, which is used for TLS/SSL cryptography. It is used to secure websites such as HTTPS security. And an example of the website may be anyone such as www.google.com. And another certificate type is the self-signed certificate, which is internal or for test environments, and it is can be used inside an organization on intranet. So inside organization, each entity trusts another one. So the internal certificate or self-signed certificate can be used inside the organization on network or intranet. So this is a certificate trust chain. So root CA to intermediate CA and to the end entity such as website or individual certificate. So the root key is kept offline and only used to sign intermediate CS. Browser trust certificate issued by vetted CS. So certificate validation methods include CRL, which is certificate revocation list, and this is browser-based browser download list of revocated certificates. So this is, you can say, an old method where the browser would download all the revoked certificate list. It would be a long list. Another efficient method is OCSP, which is Aligned Certificate Status Protocol. It is real time and it shows good, revoked, or unknown status check of the certificates. And you can also use the validation method of PIN or internal list. It is used by some browsers such as Chrome for faster validation. So key takeaways from the PKI is that PKI is equal to trust plus verification plus revocation. So PKI first, it is built on based on trust of CAs, trust of CS certificate. Then it has the verification method of the certificate, and finally, if a certificate is no longer used or it is compromised, it is revoked, and it has a certificate verification method such as these. Security depends on keeping private keys secret for both the user as well as the CA. Compromised keys are untrusted CAs are potential for man-in-the-middle attacks. So certificate check ensure the trust inheritance. So what are digital signatures and digital certificates? Important topic. So the purpose of digital signature is to provide authentication, integrity, and non-repudiation. So digital signatures basically do not ensure confidentiality. For confidentiality, we use encryption. Digital signature only provide authentication of a user, integrity of message, and non-repudiation of user or systems. So how does digital signatures work? So first, the message is hashed to provide a message digest using a hashing algorithm. For example, you can use SHA-2. Then the hash message is encrypted with the sender's private key, and this constitutes the digital signature. So digital signature is the hashed message and encrypted with the, you can say, the private key of the owner. This constitutes the digital signature. So when the digital signature is received by the receiver, it again hashes the received message again. So at the receiver end, both the message as well as the digital signature are sent. It decrypts the digital signature using the sender's public key, and then it compares both the digest that was received through this signature. When decrypted using the public key, the hash message is received, and hash of the message received is also taken. Both they are compared, and if they match, it means message is authentic and unaltered. Trust and verification. So receiver must trust the sender's public key, and trust is established by direct key exchange or certificate authority, as we studied, verifying the identity via digital certificate. The best practice is to use the private key only for signing and not for message encryption. What are some vulnerabilities inside digital signature? These may be hash collisions, which means when two messages produce the same digest. So ideally, each message should result in a different digest, but if two different data messages or text messages produce same digest, it means we have a hash collision. Private key disclosure. If private key is compromised, it invalidates the authenticity, and CA compromise, so it allows attackers to spoof identities and forge signatures if the CA is compromised. So how to mitigate these vulnerabilities? Use strong hash algorithms, protect private keys and revoke compromised ones through add them into CRL. Trust only reputable and secure peers. Non-repudiation. So non-repudiation ensures that a message or transaction cannot be denied by the sender, proving it originated from a specific entity. It means it provides or ensures authenticity, that a message is sent by a specific user and that user cannot deny that he or she sent the message. So it is essential for contracts, legal documents, banking, and supplier orders. So how do we ensure the non-repudiation? It is how it is achieved. So the originator signs the message with their private key. Remember, the private key is always with its owner only. The recipient verifies using the public key of the sender, or public key of the originator, confirming the sender's identity. Private key potential is protection is crucial. Compromise destroys non-repudiation. So if the private key is lost, it means non-repudiation can no longer be ensured. So here, as we saw, that if the user signs the message with the private key, it can only be decrypted. Sign means it is encrypted with the private key. It can only be decrypted with the public key of the this private key pair. So if this is the party A, this is party B. Party A signs the message with his private key. It can only be decrypted with the public key of the same private key pair, that is the party A public key. And if it is decrypted, it means it proves that the message was indeed signed or sent by the party A. So risk with the non-repudiation are that private key disclosure, which allows attackers to forge messages and fake money transfers, and PKI compromise. Attackers spoof trusted identities. For example, an incident of Notar, which was a CA and whose certificate were compromised, and then attacker used them to spoof identity. So how to mitigate these risks? Use trusted timestamps as per RFC 3161 from a time stamping authority, that is TSA, to prove when a message was signed. Promptly revoke compromised keys and trust only secure certificate authorities or CAs. Blockchain and non-repudiation. So blockchain is a decentralized, tamper-resistant ledger secured by cryptographic hashes. Any change requires altering all subsequent blocks, making forgery nearly impossible. Used for traceability and accountability industries like supply chain management. For example, it is used by the Ford. Integrity. So, how do we ensure integrity through cryptography? Integrity ensures that data has not been altered or tampered with. A key component of the CIA triad I is for the integrity. So, how integrity is verified? Apply a hash to a message to generate the hash, or you can call it hash 1. Recalculate a hash of the same message later and compare it with a H1. So the hash is again calculated when the message is sent and received at the receiver end. If both the hashes are equal, it means the data is unchanged. If not, it means the data was tampered during transit or transfer. Integrity, so checksum versus cryptographic hashing, what is the difference between them? So checksum are simpler math function, for example, sum of bytes. Cryptographic hashes are complex and it is based on one-way algorithm. Checksum basically detect accidental errors while cryptographic detects intentional tampering as well as other transitional or transportational alteration as well. Uh, Checksum is easy to forge. Attacker can recalculate the checksum, but cryptographic hash are extremely hard to forge or find collusion. What does this mean? This means it is very difficult to calculate the same hash from a different message or to guess the message from the hash, because it is irreversible, it is one way. You can transform a message to a hash, but you cannot go backward. You cannot convert the hash to the message. An example of checksum is loan algorithm for credit card, while example of hashes are SHA-3 and SHA-512. So hash collision, as we studied, it occurs when two different messages produce the same hash. MD5 is now considered cryptographically broken due to collision vulnerabilities. So MD5 should no longer be used. The secure option are SHA-3, SHA-512, etc. What is HMAC? That is hash-based message authentication code. So HMAC basically adds a secret key to the hash process. So in this way, it verifies both the integrity of the message as well as authenticity or the origin of the message. So HMAC is used in TLS, transport layer security, and IP security VPNs. It still requires key sharing between sender and receiver, because in symmetric method, the receiver and sender both have the same key. So what's the difference between digital signature and HMAC? So HMAC uses shared secret key, while digital signature uses private and public key pair. HMAC provides integrity plus authentication, while digital signature provides integrity, authentication, and non-repudiation. HMAC is lightweight and no PKI is needed to implement it, while digital signature requires PKI and has more overhead. So now coming out our another important topic, methods of cryptanalytic attacks. What are some attacks that are carried out against cryptography? The first one is the brute force, where attacker tries all possible keys until the correct one is found. And defense against brute force is to use longer keys length, for example, AES 128. You can use a longer one, AES 192 or 256. Password protection use slow hashing, that is PBKDF2, bcrypt, and salting to defeat pre-computed attacks, that is Rainbow tables. So as we already studied in our previous slides, that when we use salt and pepper with password, it means that our hashes for the same password, even if two user has the same password, their hashes will be different due to salt and pepper, and thus we can protect against the rainbow tables attacks. Ciphertext only attack, where attacker only has encrypted data and tries to deduce the key or plain text. For example, web, which was previously used in Wi-Fi, wired equivalent privacy is vulnerable due to weaknesses in RC4 stream cipher. So defense against the ciphertext only attack is to use strong encryption algorithm such as the latest standard WPA3 in Wi-Fi. Number three is the non-plain text attack, which is when attacker knows part of the plain text and its corresponding ciphertext. For example, German Enigma known phrases helped break the code inside World War II. So defense against such attack is to avoid predictable plain text patterns. Number four is chosen plain text attack. When attacker, it is the type of attack when attacker can submit plain text and get its ciphertext. For example, World War II Midway AF message test. So this was the message sent intentionally in clear text, you can say, by the Allied forces. It was then received by the German forces and sent through their Enigma machine in encrypted way. So when the encrypted message was received, the ciphertext for AFR reduced, and thus they were able to break the German Enigma. So defense against them is to use modern algorithms with randomized encryption. Number five is chosen ciphertext attack. It is when attacker can submit ciphertext and obtain plain text. For example, this attack, Bleichen-Baker attack on SSL 3.0, which is an RSA vulnerability, and defense against it is to use updated TLS version and constant time error responses. And number six is frequency analysis, which exploits character frequency patterns, and it is useful in substitution ciphers. And defense against it is to use modern ciphers with no character correlation. And number seven is implementation attacks, which exploit flaws in software or hardware in implementation, not the algorithm itself. And defense against is to follow secure coding and patching practices. Number eight is side channel attacks. In this attack, the attacker derive information from timing, power use, cache, or electromagnetic emission. Example include Spectre and Meltdown, that is cache timing, and defense against it is to use constant time algorithm and shielding. Number nine is fault injection. So in this type of attack, intentional hardware or software errors are injected to reveal the key data, and defense is to add error checking and redundant verification. Number 10 is timing attacks, which analyze encryption decryption time to infer keys. Defense is to implement isochronous, that is constant time processing regardless of the key length. And number 11 is man in the middle attack. So the attacker intercepts and alters communication between two parties. Example is DigiNotar Certification Authority compromise in 2011, and defense is to use valid digital certificates PKI and certificate pinning. And number 12 is pass the hash, where attacker reuse a stolen password hash to authenticate. And defense is to use least privilege password rotation and multi-factor authentication. Number 13 is Kerberos exploitation, where attackers forge or reuse tickets known as pass the ticket attacks. And defense is to use multi-factor authentication, monitor Active Directory logs, and enforce strong passwords. Number 14 is ransomware, where ransomware is the malware that encrypts files inside your computer or server and demands a ransom for the decryption key. Defense is to maintain offline backups, apply patches, and use least privileges, as well as update the anti-malware. So our next topic is the site and facility design. We are talking about physical facility that houses your infrastructure, such as your data center. And the core principles for the site and facility design are to apply CIA triad even to your physical environment. So confidentiality slash integrity, it prevents unauthorized access, theft, and tampering with your IT equipment. Availability principle prevents downtime from environmental disasters such as fire, flood, and earthquake, and infrastructure disasters such as power or HVAC failure events. Also apply risk management mitigation techniques, as we studied, maybe to avoid the risk, which is to choose low risk location for your facility or design. For example, you can choose a location that is not prone to earthquakes, tornadoes, etc., so that you can avoid such physical natural disaster. Mitigate is to apply physical controls, such as you can apply the physical access control, you can apply guards, you can apply biometrics, so that only authorized personnel can enter the facility. Transfer is to use insurance or vendor contracts to secure your facility, and accept is the residual risk within the tolerance. Wiring closets and intermediate distribution facilities. So you should secure the wiring closets and intermediate distribution facilities from unauthorized or accidental access. So avoid the wiring closets, avoid locating them near pipes, HVAC, or electrical equipment. Use racks and shielding against water and electromagnetic interference. Ensure proper ventilation to prevent overheating of the equipment. And protect network, alarm, and door lock cabling that extend beyond controlled areas. How to protect server rooms and data centers. So adds four main risk areas. That is the physical access to the server room and data center, HVAC and utilities, environmental threats, and fire risk. So implement controls for personnel. You should always do the background check of the employees before onboarding and before hiring. You should do their training, and you should regularly monitor the access logs to your facilities, maintenance, routine testing of the HVAC as well as other infra facilities such as generator, UPS, and fuel should be done. Monitoring and auditing, continuous logging and alerting of all the physical access to your facility. So refer to these standards when implementing these site and facility controls. So next is the media storage facilities. So always maintain temperature and humidity control, air filtration, and anti-static flooring, avoid magnetic fields and allow media to acclimate before use. So media means by media storage facility means that our backup location where we store our, let's suppose, storage area network, maybe we store our HDDs such as these. So as we study that magnetic disk drive are can their data can be erased when exposed to strong magnetic fields. So you should avoid magnetic fields near these facilities. Implement tracking and dual authorization for media handling. Use fire detection and suppression, proper housekeeping, and dedicated storage areas. Consider off-site storage for disaster recovery and enforce media sanitization and destruction before disposal, such as degassing if you have the magnetic disk drive. Evidence storage, how to protect the evidence storage facility. So maintain chain of custody with tamper-proof logbooks, restricted access policies, video monitoring may be motion and sensor based, dual log or door control system. So the purpose is to ensure authenticity and integrity of evidence for legal use. Restricted and work area security. So it is designed based on risk assessment and threat modeling and applies principle of least privilege, need to know, separation of duties, dual control, defense in depth, and compliance obligations. So it more directly impacts employees and daily operations. So now coming out to these principles, least privilege and need to know means that access be granted only as necessary for job duties and based on formally approved policies. Access rights must be reviewed regularly and maintain auditable records of access decisions and reviews. Separation of duties and door controls for sensitive areas require two or more authorized individuals for access, enforced via administrative control, for example, guard log, surveillance review, technical controls such as dual lock, multi-factor access systems, and reduce insider threat and fraud risk. Defense in depth means to use layered security zones. For example, you can divide the areas into public area, which is exterior, lobby, or reception. Low security is general office space, and high security areas are data center, labs, or restricted rooms. Each transition between these zones should require authentication, for example, reception verification, access badge, PIN, and biometric scan. So the stricter the zone, the stronger the authentication required. So the utilities and HVAC, so power and HVAC systems are critical to data center reliability. Both must be designed from a risk assessment perspective with redundancy, testing, and maintenance plans. And these are the power redundancy level. These are different tiers, and this is their availability rating. So tier 1 has 99.671 availability and it has no redundancy and include multiple single points of failure. Tier 2 has 99.741 availability and it has partial redundancy known as NUPS. Tier 3 has 99.982% availability. It has N plus 1 UPS configuration, means it allows maintenance without downtime, and tier 4, the highest tier, has 99.995% availability and it has 2 NUPS and has full redundancy and there is no single point of failure. So N here stands for sufficient units for full load. So N plus 1 means 1 extra for maintenance or failure, which is tier 3, and 2N means that we have fully redundant independent system. For each UPS we have a redundant UPS so that if one fails the other still continue to provide the necessary power. So some power consideration, UPS types may be battery based, which varies by load, capacity, filtering, and reliability, and they may be flywheel based, which is better for high loads greater than 200 kilowatt and short term reliability. The generators provides long term backup during power loss. So remember, UPS is for short term power provision during generator switchover, while the generator are for long-term power outages and they run on diesel, gasoline, natural gas, or hydrogen and must be tested under full load regularly. What are some lessons learned? So avoid single point of failure. For example, never use a single generator. There should be at least two, so that if one generator fails, the other can be used to provide the necessary power. Test for real life duration, not just short runs, and identify external dependency, for example, cooling water. Cooling and humidity. So maintain redundant cooling units N+1 or higher, prevent rapid temperature changes. For example, the temperature change should be less than or equal to 5 in an hour. The tapes are less than equal to 20 centigrade per hour without tapes. Control humidity. Low humidity produce static discharge risk, and high humidity has the condensation risk. Maintenance best practices include scheduled maintenance and full load tests, fault detection and alerting system, periodic audits to ensure reliability. So environmental issues include natural, internal, wildlife warming, or pandemics. So the natural may be storm, earthquake, floods, fire, and mitigation includes site selection area, building design, and disaster recovery plan. Internal may be leaks, burst pipes, condensation, and mitigation include equipment placement and drip canopies. Wildlife warming include cable damage and short circuits, and mitigation includes sealed cabling and regular inspection. And pandemic example is the workforce unavailability, and mitigation include remote work, flexible staffing, and hygiene policy. So, fire prevention, detection, and suppression. So, fire principles are that fire needs heat, fuel, oxygen, and chemical reaction that are also known as fire tetrahedron. So, suppression of fire removes one or more of these elements. For example, if oxygen is removed, fire won't be able to go on. So you should the purpose of fire suppression is to remove any of these elements. So fire suppression systems types, description, and pro and cons. So the wet pipe sprinkles, the pipes are always filled with water in this type of suppression system, and their pros and cons are that pros are they are low cost, and their cons are that they have the risk of water damage. Dry pipe fire suppression system are that water are released only when triggered, and it is for colder environment, and a con is that it has a delayed response as compared to wet pipe sprinkler. Deluge is all heads are open, and it releases large amount of water, and it is used in industrial areas. Reactions are required both detection and heat, and it reduces accidental discharge. Water mist are fine droplets, less water damage, and it is better for electronics. And some clean agents for fire suppression systems are CO2, halon, HFC-227EA. So gas basically displaces oxygen or stops chemical reaction, and it has no residue, it is costly, and has safety consideration for humans. So fire extinguisher, use correct extinguisher type. Wrong one use can worsen fire or endanger staff. So these are the classes. They are important to remember. Class A is for solid materials such as woods, paper, and plastic fires. You can remember A from ash. So these are the things that produce ash, and for this we use class A corresponding to ash. Class B is used for flammable liquids and gases. Class C for electrical fires or electronic fires. Class D for combustible metals. And class K or F for cooking oils and fats. So staff for safety training know all exit and extinguisher location, understand when how to use extinguisher, know how to manually activate or delay suppression system, be trained to power down equipment safety and maintain good housekeeping. No storage or cardboard should be the server rooms. So that's all for this domain. This domain was lengthy and I must be honest, I just went through this domain very quickly without much explanation. But that will not be the case for the upcoming domains, specifically the domain 4, which is my specialty, the network and the communication domain. So stay tuned and we'll see you in the next domain.